Hello, my name is Martin Fuller. I am an engineer with Microsoft's Advanced Technology Group. This talk on variable rate compute shaders assumes a basic understanding of variable rate shading, and in particular the tier 2 screen space image, where for every screen space tile we have decided upon a shading rate to be used by the pixel shader. Specifically, this talk then extends that concept to compute shaders. We will have a particular emphasis on implementation details on the Xbox Series consoles, and we will be assuming 2x2 as the coarsest rate, although it is possible to extend this technology to 4x rates. So firstly, I will be covering the motivation for variable rate compute shaders. I will be talking about an initial implementation that is shipped in Gears 5. I will be talking about a more advanced implementation that respects coverage, and finally I will be talking about variable rate shading deblocking as a post-process. So, variable rate compute shaders. What is our motivation for this new technique? So, in any engine, what we want to do is minimize the cost of lighting. And in particular, when ray tracing is involved, the cost of lighting has gone up considerably. So with variable rate shading, if you have a forward lit title where the lighting has been done in your pixel shader, then variable rate shading automatically gives you that benefit in this case, because you are reducing the number of pixel shader threads. And if you have a full depth prepass, then with variable rate shading, your number of pixel shader threads will be, in most cases, less than the number of pixels. And that is a real performance win, and we've seen that already in Doom Eternal. And the key thing, of course, here is that that reduction in lighting calculations is only done in areas of the screen where you really can't see it. You don't notice. If you really need to be running a pixel shader thread per pixel because you have some high frequency detail, because you have high frequency lighting, then you can still do that with variable rate shading. And titles have observed an actual increase in quality from variable rate shading, and that's because the savings allow dynamic resolution scaling to hit a higher resolution. However, a lot of games use what is called deferred lighting, and in this case variable rate shading gives no reduction in lighting calculations. What's happened here is that we've reduced the frequency of writing out GBuffer elements. So we have for multiple pixels the same normal, the same albedo, the same material data, and lighting all of this is pretty much a waste. You get a slightly different depth and a slightly different view direction to the pixel, but it really is wasteful. So our goals with variable rate compute shaders, top goal is always quality. We want to reduce the cost of the number of lighting calculations, even for deferred lit titles, but we don't want to sacrifice quality to do that. The light list, so we often divide the screen into tiles, and for each tile we have a list of lights that's consistent for that entire tile. We need that to be invariant, so every pixel is processing the same light, and we're not diverging on different light properties or different light types per pixel. As well as lighting, deferred lighting, we would like this technique to be applicable to many other lighting passes or full screen passes. And there needs to be a low fixed overhead, so even in the case where most of your screen is running at 1:1 rate, we don't want this to produce a net loss. Finally, while I'm going to focus on variable rate deferred lighting, that's a bit of a mouthful, so I may refer to this as sparse lighting for the remainder of the talk. So the very first implementation that I'm aware of has actually shipped in Gears 5. Thank you very much to Christopher Wallace and the team at the Coalition for allowing me to share the basic details of how this worked. So Gears 5 had an implementation of screen space global illumination that was running with a variable rate compute shader. And the way this worked is they would dispatch the full number of waves to process the entire render target as normal. And then per tile, they would read the shading rate image that was driving variable rate shading. Then, depending on the shading rate, they would reduce the number of waves required to process that tile if there was a coarse shading rate involved. And correspondingly, this increases the area that a single wave or thread will process. So a single thread might be processing just 1 pixel in the full rate case, or anything up to 4 pixels in the case of 2x2 rate. They would then calculate the screen space global illumination, and we would then perform hole filling, where we're copying the results horizontally and or vertically. And this is pretty straightforward, easy to implement, but obviously it doesn't respect triangle coverage. So here is some straightforward pseudocode. So at the beginning, we work out exactly how many waves are required to process this particular tile. So the shading rate is the shading rate for the tile. And then if this wave isn't required to do any work, then it can early out, go back to the pool. Another wave will be reissued, and that will hopefully find some useful work to do. And then the remaining waves will do their calculations, and then they get to this hole filling pass where each thread is writing out the calculated color, and then if we need to copy that color horizontally, vertically, or both, then that's done as a post fix to your original shader, as you see below. So here is a scene from Gears 5 that is using variable rate screen space GI, and one of the things you should take away from this is that you don't see any bleeding of the GI values across surfaces. And here is the SSGI buffer from the same scene, and we can see here that the outlines of the various objects are in fact very crisp. It would be extremely hard to look at this image and say that we weren't in fact perfectly respecting coverage. So in theory, of course, we're not respecting coverage and the edge of one triangle going onto the edge of another. And in theory, yes, this creates a subtle quality issue, but it's actually incredibly hard to spot. And there's two main reasons for this. First of all, SSGI is very diffuse by its nature. Secondly, if there was a discontinuity in the original image, then we would have been required to run this at full rate in that axis, whether it's horizontal, vertical, or both. So that means that in the case where you have a discontinuity in the surface itself, then you'll be running the SSGI at full rate in that axis. And of course, there are many times where you can lower the shading rate and coverage doesn't matter. This is particularly when you have blurs going on. So this could be motion blur or depth of field, where the values from different surfaces and different triangles are getting blurred over each other anyway. And of course it could simply be dark or heavily fogged out. So Gears 5 was actually hitting its performance targets even without variable rate compute shaders. So the variable rate SSGI did not ship on console. They did not need it to hit the performance targets. So it was limited only to the performance mode on PC for an extra performance boost. There is actually a very simple extension to the Gears 5 technique where, although you're not respecting coverage while you're producing the values, so your values are being produced at a low rate, you could respect coverage at the point where you're doing the hole filling. So for example, if you're rendering clouds at a low rate, for example, because this particular screen tile, the clouds are are extremely diffuse, there's no outline. You can then copy that result onto the render target, but you could do a simple check during halve filling to say, is this pixel sky or not? And if not, don't write the sky color. So this makes the technique more attractive. There are more uses. So the remainder of the talk will cover some research I've been doing in, again, variable rate compute shaders, but now respecting triangle coverage, so we'll get no leaking between different triangles. So the process here is to find out what duplication and pixel values variable rate shading actually achieved when the pixel shader was being run. We then need to process only a subset of the pixels, again for deferred lighting as our case here, but it could be any deferred pass. And we're going to end up with 1:1 rates where we want to run a lighting calculation for every pixel. We have the two half rates, 1:2 and 2:1, where we're going to run one lighting calculation for up to 2 pixels, and 2:2 rates where we're going to run one lighting calculation for up to 4 pixels. And this up to is the important point. This is where coverage comes in. We then have a bunch of pixels that we didn't light, so we need to go halve filling. And then per frame, as an optional step, we would like to be able to rotate which pixel is lit and which one is the hole that gets filled in with a duplicate value, and let temporal anti-aliasing come and fix our sins for us. So the real crux of the problem that I had to go and solve was this idea that the shading rate that you ask for is not necessarily the shading rate you get, and this is again due to coverage. So the easiest way to explain exactly what I mean is by example. So here we have a green triangle and we have 4 pixels that totally contains within this single triangle, and we're running with 2:2 shading rate. So we execute the pixel shader just once, and the result is copied to 4 pixels. And in a deferred pass, I want to pick one of these 4 pixels, light it, and then copy the results to the other 3. So this is obviously going to be an extremely good win if we can achieve it. So here we have the same 4 pixels, but in this case our green triangle is slightly smaller and it only covers 3 out of the 4 pixels. So we're still running the pixel shader at 2:2 rate. The pixel shader gets invoked, we produce a value, but in this case it's copied to only 3 out of the 4 pixels, even though the shading rate is 2:2. So we can see here that writing the shading rate to a GBuffer is not particularly useful. What I need is an alternative way to identify very quickly which of these pixels I'm going to have to light. So I need to light the blue pixel, and I need to light any one of the 3 green pixels and copy its result to the other 2 green pixels. So I need a fast way of working out the set of pixels I need to light and the set of pixels that can be copied. So the first solution is something I've previously presented at GDC 2019 in DirectX variable rate shading, a deep dive. So I'm not going to go into it in any great depth here, but the obvious and first thing I tried was select GBuffer Examination, which is obviously expensive. You don't want to examine all GBuffers, or perhaps you can come up with some kind of sharing ID. But we can do better than that, and researchers moved on. So I came up with 2 different solutions that didn't require GBuffer examination. The first is export specific. So we have a compute shader that is reading compressed depth and writing out uncompressed depth. And when depth is compressed, if 2 pixels have the same index into the plane equations, then they're from the same source triangle. And this is exactly what we need. This is coverage. So I can modify this shader to write out all the data we need for sparse lighting. So that's the pixels to go light and the hole filling that needs to be done afterwards. And this is extremely cheap. This added only 28 microseconds to the cost of this compute shader. I also wanted another method that was not Xbox specific or would work with uncompressed or expanded tiles on Xbox. And the solution here was that SV coverage has been expanded into the coarse domain by the variable rate shading specification. So this actually requires 4 bits of GBuffer space, but it is extremely fast. Not as fast as the Xbox specific, but only 153 microseconds to build this buffer of pixels to go in light. So I'm going to talk about SV coverage and how we pack this into 4 bits of a GBuffer somewhere. So looking at the spec for variable rate shading, what we see is that in the coarse case, where we have 1x2, 2x1 or 2x2, we're using up to 4 bits for was that pixel covered or not, which is exactly what we want. So we can, and for 1x1, we would obviously, it would be covered if the pixel shader was being run. What you might have immediately noticed is that there's a slight problem here, in that the same 2 bits can mean different pixels depending on what the shading rate was. So here we see 1x2 is using the 2 least significant bits to mean pixels that are vertically adjacent, and for 2x1 rate we're using the same 2 bits for pixels which are horizontally adjacent. So here we have a bit of a problem potentially. So the good news here is if a title is only using the tier 2 screen space shading rate image, then every screen tile, that's 8x8 on Xbox Series consoles or potentially larger on some PC parts, every screen tile will have the exact same shading rate. So we're only interested in our 2x2 pixels, and do we have to go light 1, 2, 3 or 4 of those pixels, and how do we do the hole filling afterwards? That's all we care about, our 2x2 pixel block. So within our 2x2 pixel block, if we're only using tier 2 VRS, then we're not going to get a mix of shading rates. So the fact that different bits can mean different things for different shading rates doesn't affect us. So the comparison becomes extremely simple. We can share a lighting calculation if we have a low rate in that axis, whether it's horizontal, vertical or both, and we have the same SV coverage value, then we can share lighting calculations. So this is extremely fast and simple. Where things become more complicated is if a title mixes tier 1 and tier 2 VRS. So we have a shading rate per screen tile, but we also have some triangles that might have picked a different shading rate to what the screen tile selected. And in here we have to be able to disambiguate between the 3 shading rates. In fact, this isn't too difficult to do, and in our Xbox specific sample we have a function, get quad coverage, that does this, that disambiguates between the bits before it stores them in the GBuffer. So what we end up with is we have a compute shader, and that is examining compressed depth and or these 4 bits of GBuffer space, and it's going to output per screen tile the number of lighting calculations we need to do, and then for each screen tile the XY coordinate of that lighting calculation, with 3 bits of whether to then copy it horizontally, vertically or diagonally. And in fact that left me with 21 bits spare, because per 16x16 screen tile I only needed 4 bits for X, 4 bits for Y and 3 bits for hole filling. So I have 21 bits spare, which is perfectly sufficient for a UNorm Z value, which was in fact a performance win, because this allows me to skip reading the depth separately in the deferred lighting shader. So we have these 2 resources. We have a very small texture, only 240 by 135 for 4K resolution of the number of lighting calculations we have to do. And then we have this buffer with a 32-bit payload potentially per pixel, but we'll see actually managed to optimize that down to a slightly smaller count, as we'll see in a few slides. So here we have a dragon's head from the sponsor atrium being lit by 3 lights, and on the right we have the count buffer, which tells us how many lighting calculations we need to do per 16 by 16 tile. And we can see that the highest number of calculations comes in where we have some interest in the bottom left from the specular term, or from the green light, which is quite intense, and so on the right hand side of the lion's face. But what we're really interested in, of course, is the really dark regions, the blacks, where we have very few lighting calculations to do. This is where we're going to get the performance win. So why did I pick 16 by 16 tile size? You could pick anything. This seemed like a good, sensible size to me. It's a good granularity for light tile culling, as again, we want for all pixels within each 16 by 16 tile, we want to be processing the same lights, not diverging on light type. It allowed me, as I said on the previous slide, to pack in this 21 bits uniform depth. Larger sizes are better in that for every 16 by 16 tile, the chances are that you're going to have one partially filled compute shader wave that we don't need every thread to be active. So the larger the tile size, the less of these partially filled waves we're going to have. So it is a trade-off. So here's the pseudocode from Xbox that is producing these 2 buffers, that's producing the buffer of the number of lighting calculations to go and do, and the buffer of coordinates. This is specifically optimized for Xbox, where we can read compressed depth. So first thing, if the tile is clear, which we will know very quickly from compressed depth, then we have no lighting to go do. So there's an early out there. If the tile, we're reading the shading rate now, so if the tile was run at 1 by 1 rate, then we're going to have to go and light every pixel. As you saw, I was using an R8 texture, so I can't write 256, my maximum value is 255, and we'll see why that's not a problem in a moment. So again, this is an early out for that tile, we're just going to light every pixel. The next case we get into is this tile, is the depth compressed for this tile? If so, we can check the indices into the plane equations, and this is our fast path. So the more compressed depth tiles we have, the better. And we typically end up with more when we have a better front to back ordering of, say, a depth prepass. Otherwise, we're going to check these 4 bits from the GBuffer. If you don't want to give up 4 bits from GBuffer, you could just bail at this point and light every pixel. So we've checked for either the quality of the SV coverage values or the same plane equation indices, and we know our coverage, we know our shading rate, so we're going to write for every 2 by 2 pixels, we're going to write between 1 and 4 locations to go and light, and then the post copying operations, the hole filling, and then once for the entire wave we're going to write out a count into this texture, the number of lighting calculations we need to go and do. So no atomic operations there, which helps keep it fast. So in the actual deferred lighting pass, we're only going to get a performance speed up if we can have an entire wave 32 that comes in and doesn't have any work to do and immediately retires. So this means that we're only going to get a win if we have 224 or less lighting calculations to go do. So this is why we say, well, if there's more than 224 lighting calculations to do, then we're not going to read the coordinate buffer. We're just going to derive the XY of the pixel that we need to light from the thread ID, which is how deferred lighting systems currently work. That's the conventional means. So this means that anything that we store in the count map that's more than 224, we light every pixel. So this is why storing 255 into the count map instead of 256 is not a problem. It also means that the coordinate buffer only has to be large enough for 224 coordinates per 16 by 16 tile. So this allows us to shave off 12.5% of the memory of this buffer, which is turns out to be, for something like Xbox Series S, maybe the maximum resolution might be 1440p. This optimization saves you at that resolution 1.75 meg, so pretty decent. So every deferred lighting shader starts off computing the pixel XY that it's going to light and reading depth for that pixel XY. And in the case of sparse lighting, this is performed by a function. You simply call a function that takes the group ID, the group thread ID as inputs. It's outputting this coordinate, the pixel XY. It also gives you depth as a normalized value between 0 and 1. It returns whether or not sparse lighting is enabled, and then the hole filling bits that are needed to copy the result of the deferred lighting operation, whether that's horizontally, vertically, or diagonally. And the function returns a boolean for whether the wave itself has any work to do, or the thread itself. So the first thing the function does actually is it rotates the group ID. And the reason for this, I found, is that the dispatch typically is, and certainly on Xbox, is running through the render target in rows rather than columns. And if you have sky, it is simply reading the tile counts for the sky tile, finding it has 0 lighting calculations to do, and retiring the entire wave. So what I found is that by processing the render target in columns rather than rows, this got more waves doing useful work earlier, rather than backloading all the work. And this is worth 60 microseconds in my test, so this is well worth having. This does mean you've changed you swap the dispatch dimensions as well, X and Y dimensions as well on the CPU. So here we've rotated the group ID, we work out the tile, we read the count map, and then if it's sky, then we have nothing to do. Simple. The next part of this same function is the more interesting part. So here we work out whether we are reading the buffer, which has the coordinates to go light in it, or whether we are lighting every pixel. So again, we are seeing whether we have less than equal to 224 lighting calculations to go do with our wave 32s. So in the case where we are reading the buffer, then we have to work out for every thread what's the index into this buffer to go and read the coordinate X, Y, and depth and hole filling bits. And if this index is larger than the total number of lighting calculations, then nothing to do. So this return statement here in the middle is the important one, because here is where we get entire waves retiring, saying I have nothing to do, and they get recycled, and the new compute shader waves are launched, which are going to pick up work to do from a different tile. And of course, this ordinarily this condition will produce one partially filled wave as well. Chances are you will end up with one partially filled wave. So the threads that survive this check, they read this buffer, they get the 32-bit payload, and they trivially extract the X and Y coordinate, the depth value, and the hole filling bits. And of course, we don't need to read, have a separate read of depth. And then we have the case where we have more than 224 lighting calculations to do. So we compute what is essentially the dispatch thread ID, although because we rotated the group ID, we have to compute dispatch thread ID ourselves. So now we have the pixel XY simply derived, and we read depth from the depth SRV. And that's it. The deferred lighting then carries on as normal. Every thread has its XY coordinate and its depth. Until we've done with deferred lighting, we need to do the hole filling as a post step. So onto the graphics and what this actually looks like in practice. This scene is the default camera position when the Xbox sample VRS and Sparse Lighting starts up. This is what you'll see along with some debug text. So here is the tier 2 shading rate image, and we can see a lot of the mountain range that's in direct light is being run at full rate. So we're running the pixel shader every pixel, and we'll need to do a lighting calculation for every pixel as well. We have some cyan. So this is one of the half rates, which is it's full rate vertically and half rate horizontally. So this is good for steps. We also have the yellow, which is the opposite. It's still a half rate, but it's more detail horizontally and half rate vertically. So this is good for railings. And then when I've applied no tint at all to the image, this is where we're running quarter rate. So 1 pixel shader invocation for 4 pixels, and we hope to do one deferred lighting calculation for 4 pixels, though that will depend on coverage. And we can see this is being used up close and in areas of shadow. So what this sample actually implements is fairly classical deferred lighting. The main cost of the pixel shader here is the procedural albedo, which is based off the height in world space and the normal. So whether it's grass or mud or snow is all procedurally generated, and this is unfiltered, so this can produce very high per pixel variance. We're not reading a map with bitmaps, though we are in fact the normal, so the normal itself is read from a normal map. And then we do some deferred lighting, and the deferred lighting is somewhat expensive. The main expense is that we're doing ray march soft shadows. So particularly when the sun is low, as it is reasonably low in this, these rays can be quite long before they escape the scene. I mean, it's a custom ray marching implementation, but it could easily be, DXR, a ray query. Then we have some atmospheric scattering, and then we have an ambient term also being computed in the deferred lighting. So this is our count buffer visualized to show how many waves we need to execute. So the sky is black. We don't need any waves at all. Light green is only 1 wave, and this can only really occur on the silhouette with the sky, because if you think about it, if you have a 16 by 16 tile, as I'm using here, and which is 256 pixels, and you are lighting 1 in 4, which is the ideal case, then you can only get away with, you get 64 lighting calculations, which is 2 waves. So you can only get 1 wave worth of lighting calculations on the silhouette. So dark green is this case where we've got 2 waves. This only happens really with larger triangles, but we have some of that in this scene. And then we have gradation between cyan and yellow, which is 3 to 7 wave 32s that we need to light a tile. And then in red, we have to light every pixel. So fairly straightforward. So this is a useful debug view where I don't do any hole filling. So where I would have done a copy, whether that was horizontally, vertically, or both, instead I just write black. So you can see here where I'm getting the saving, where particularly in the sort of foreground and midground, there's a lot of black pixels, which are pixels I didn't light. And the only places really where I'm doing a lot of lighting calculations is this area in direct sunlight up on the right, and some of these kind of silhouette tiles, again where we've got terrain that is facing the light source. But we can see just purely from the number of black pixels present where we're getting our performance saving. So the figures on Xbox Series X running at 4K resolution. So we have on the left-hand column, we have VRS turned off and Sparse Lighting turned off. So this is the absolute ground truth. We're running a pixel shader thread per pixel to populate the GBuffer. We're running a compute shader thread per pixel to light those GBuffers. And we end up with a total time of 5.4 milliseconds, nearly 5.5. And then we have VRS turned on, which only helps the GBuffer pass. And in fact, a considerable proportion of the GBuffer pass was the procedural code to generate the albedo that we are saving on reading the normal map as well. So we got over a millisecond saving here. The time to decompress the depth buffer has gone up because this pass now is also building the sparse buffers. It's producing the count map and the buffer coordinates to go light, but only by 27 microseconds. Deferred lighting cost here has massively dropped. So we were at 2.3 milliseconds. With sparse lighting, we're down to 1.1, so 47% of the time. The rendering of the sky is not very complex. There are no clouds. A small saving from variable rate shading. Of course, with variable rate shading and variable rate compute shaders, we need to generate and set the shading rate map, which is about 0.1 of a millisecond. But overall, we've managed to halve the frame time for this scene from 5.5 milliseconds to 2.8, near enough half. So the story is similar on Xbox Series S at 1440p, and the major caveat here is that I'm rendering the exact same content, the exact same mesh LODs, and this is not something a real game would do. You would reduce your mesh LODs for the lower resolution, so we don't get quite as much of a win from variable rate shading because the triangle sizes are smaller, and we don't get quite, for the exact same reason, we don't get the same shading from sparse lighting because the triangle sizes are smaller, and therefore there are less lighting computations that can be shared within the interior of each triangle. But again, this is, I think, a very, very good saving. So the overall frame time was 7 milliseconds when we are not running with VRS and we are deferred lighting every single pixel. With VRS on, again, GBuffer we've saved, we're down to 56% of the time. Deferred lighting, we saved 1.2 milliseconds, we're down, which is 55% of the time. So overall, we've saved 59% of the time. We're running in 4.2 milliseconds instead of 7.1. So this is this is an extremely good saving on Xbox Series S as well. And again, just to highlight that the Xbox Series S is running the same mesh LODs, and therefore the triangle sizes are much smaller, and you can see here exactly what that does to the count buffer. So the number of lighting calculations we have to do has gone up, and significantly so in the number of full rate tiles where we have to light every single pixel. So as I mentioned, the main, or one of the most significant costs of the deferred lighting is the shadow ray, and this is a soft shadow, and here we're doing ray marching rather than ray tracing, but that doesn't particularly matter. So as I previously mentioned, the closer you are to sunrise or sunset, the more expensive your shadows get, because the longer the shadows and the more geometry the ray will have to traverse until it escapes the scene, or perhaps even hits something. So you can typically expect that, yes, a horizontal sun is much more expensive than an overhead vertical sun. The interesting thing here is that sparse lighting is significantly reducing the variance between those best case and worst case scenes. So here is a comparison table. So the ground truth again is that we shade every pixel and we light every pixel. So with a horizontal sun, again, Xbox Series X at 4K, horizontal sun, 10.5 milliseconds, down to a low sun angle, so a bit higher you might say, 5.4 milliseconds, and sun raised again, 3.9. So the variance here between horizontal and a high sun angle is a huge 6.6 milliseconds. You know, that it really gets expensive when the sun gets down horizontal. However, with variable rate shading and sparse lighting, the lower the sun gets, the more 2x2 rate we have, because the more stuff is in shadow and therefore can be shaded at a lower rate. So this is helping that worst case considerably. So we can see here that the horizontal case is only 4.8 milliseconds, so it's less than half the time. And then the low sun's 2.8 and the higher sun is 2.2. So the variance between the worst case and the best case is only 2.6 milliseconds instead of 6.6. So this is really good news in keeping a consistent resolution, particularly if you have DRS. And if you don't have DRS, this helps you to draw more at those lower sun angles without dropping frames. So that was performance. Now the all-important quality, which was my #1 consideration. In fact, when doing this work, that we had to be able to show a performance win, but not at a reduction in quality. The sample actually implements rotating which pixel is lit every frame, and it does that at 0 cost, but it doesn't implement temporal anti-aliasing. So for the purposes of quality comparisons, you might not want to turn that on. Of course, the only difference that we get when variable rate shading has output identical values to the GBuffer, the only difference you would get between adjacent pixels with identical GBuffer values is a very slight difference in view direction and a very slight difference in depth. But you should remember these are, when they're sharing lighting calculations, these are from the same triangle, so the depth values won't be very different. And the key thing to remember here is if your scene contains some kind of very strong specular aliasing, specular highlight, then you should be running at full rate. Variable rate shading should have picked 1:1 rate. Therefore, we would be running the lighting at full rate as well. And this is one of the reasons that I didn't bake the albedo into texture, because the texture would have been filtered. So that is unfiltered to see if we can maintain the quality. So here is our opening test scene again, and there would be absolutely no point in me toggling images to let you see the difference. They're really impossible to see the difference without zooming in. Well, in fact, even zooming in, which I'll show right now. So we're going to go for 16 times magnification and have a look at this small peak here. So here we are at 15 times magnification, and I've actually left the debug text visible this time to show that these are in fact different images, and I'm not accidentally showing the same image on multiple slides. But here we have a 16x magnification of this peak with the shading rate shown in debug. So we have a lot of high rate stuff here, which is either because it's being lit directly by the sun and we have a lot of interesting stuff going on, or because it's actually on the silhouette on the top right there, and I'm not testing depth discontinuity in this case, which would reduce the shading rate. But the main takeaway here is we have a lot of stuff running at full rate, but we also have a lot of stuff that's not tinted, which is running at 2x2 rate, and a small amount of the half rates, the yellow and the cyan tints, for 2x1 and 1x2. So here we have variable rate shading is turned on, and we are lighting every pixel. So this is very much the situation that something like Gears 5 is in, where we have variable rate shading running, and it's giving a good win in laying down the GBuffer and some of the post passes like SSEO, but deferred lighting is still running every single pixel. So our total time for the scene here is 3 milliseconds, and our deferred lighting time is a good chunk of that at about 1.6, 1.7. And here we have the exact same view again, still at 16 times magnification, but in this time we are running both variable rate shading and sparse lighting, and you can flick the video back and forth and look at the before and after between lighting every pixel and lighting a subset of the pixels, and I challenge you to see any kind of a difference. But what we're accepting, of course, that the deferred lighting time has dropped significantly, which is brilliant. That's exactly what we're after. So here's a side-by-side comparison. In both cases, variable rate shading is turned on. On the left-hand image, we are lighting every pixel. On the right-hand image, we're running sparse lighting. And we're going to call out a few features here again. And we can see this area in direct sunlight on the left. This is running at full rate lighting in both cases. So we're not getting any kind of a performance win here, but we need the quality. An important quality consideration was that we shouldn't lose per pixel artifacts. Really small amounts of detail shouldn't be wiped out or have any kind of temporal stability problems under this technique. So we have exactly that here, and again this is produced by the albedo to a large extent, not being filtered. But it could be anything. It could be specular aliasing, for example, and the technique is preserving that. And of course, these areas are where we're getting the real win. This is where we've reduced both the frequency of shading, so we have identical GBuffer values laid down by the pixel shader, and then we've reduced the frequency of lighting as well. So you can see that within these areas we have this blockiness, this BRS squares artifact, which you can't see without magnification. And in the case where we're not lighting every pixel, you can see that in fact the result is identical to on the left where we are lighting every pixel. So for completeness, here are the two debug visualizations for this same scene. On the left is the number of wave 32s required to light each 16 by 16 tile. And on the right, we have the debug mode where if I'm lighting a full rate tile, we get the values unmodified. If a tile is sparse lit, so some pixels are lit and some pixels are not, the lit pixels are oversaturated, so they're brighter, and then the pixels we didn't light in this debug mode are black, and these would have had received a copy from a neighboring pixel. Randomly picking just one 16 by 16 tile in this image, this one required 7 wave 32s to light, so the 8th wave was able to skip out and be repurposed elsewhere in the image to do some lighting somewhere else. So the top two tiles, 8x8 tiles within this 16 by 16 tile, they were a low rate. We had one 2x1 and one 2x2 rate. So this is where we're getting the saving. In fact, the bottom two tiles, we have some high frequency detail in here, some pixels that are single pixel snow. It could be single pixel specular reaction. It doesn't matter what caused those pixels to stand out, but variable rate shading decided that these two tiles had some important detail and they had to be run at full rate. So even though we have two full rate tiles here, we've managed to get a saving of one wave within the 16 by 16. So another key consideration was that this should be something that's easy to retrofit into an existing engine. We should not have massive amounts of intrusive code. So we had to make two modifications to the Deferred Lighting shader. The first was a prefix function, and all it does is it obtains the coordinate of the pixel that we're going to light and depth, and then a postfix function which does the whole filling after. And the key point here is that the deferred lighting code, or whatever your deferred pass is doing, whether it's SSR or SSAO or whatever, fog, is not otherwise modified. You just have some threads come in, they've already got their pixel X, Y, and depth, and off you go. We do need one spare vector general purpose register, to use AMD parlance, and that's storing the 3 copy bits for whether we are copying the end result horizontally, vertically, or diagonally. It's possible that you could store this to group shared memory if you wanted that register back, or you could use the other 29 bits of that register for something else. So this is what your deferred lighting shader will now look like with this modification. So at the very beginning of it, we have this call to the sparse lighting prefix function. As I mentioned, this is obtaining the coordinate to light, the XY coordinate. It's obtaining depth, and then we have this boolean, which is a scalar for whether sparse lighting is enabled, and this sparse data, which is the 3 copy bits. So we call this function. If the wave or thread has nothing to do, we return. So this is the all-important optimization when an entire wave can return out and not proceed. Then we have your shader, deferred lighting. It's exactly as it was before, completely unmodified. You have your coordinate and your depth, and off we go. And then right at the end, we have this postfix function we call, which is doing the hole filling. And here it is. Here's the hole filling function. So it's taking in our UIV. It's taking in our scalar for whether sparse lighting is enabled. It's taking in our 3 copy bits, our coordinate, and our end color. And we have a very simple trick here, which is that we XOR into the pixel coordinate for the copy coordinate. We XOR it with 1, and this will say, if we're copying it horizontally, we need to convert an even coordinate to an odd, or vice versa. Same with the vertical, whether we need to convert an even Y coordinate to an odd for the copy, or vice versa, and then we have the diagonal copy. So we're at these macros are checking these 3 bits, and that really is it. So as I mentioned briefly, the tile size for Xbox Series consoles for VRS is 8x8. For PC, that's variable. You have to query it from the device. And up until now, I've been using that same 8x8 tile size for the shading rate image for sparse lighting. But there's actually no requirement to do that. We could use a smaller tile size for sparse lighting, as that's entirely a software technique. And there's often something in the image, something within an 8x8 block, some feature that promotes the entire tile to high rate, whereas in fact the entire tile doesn't need to be at a high rate. So for this example, using 2x2 tiles, I picked a slightly different view of my test world. This one's been selected to have more high rate tiles. You might see that there's not much in the way of shadows. That's because the sun is pretty much directly behind the camera. So every pixel we're looking at has an expensive ray that's heading towards the sun, towards the camera. It doesn't hit anything, which makes it expensive because it keeps traversing. And here is the visualization showing how many of the 8x8 tiles are a high rate, which is the red tint. Quite a significant proportion of the screen. So here we're comparing 8x8 tile size, which is needed by the hardware VRS on Xbox Series consoles. This is the top left image, and the number of lighting calculations for 8x8 tile sizes in the bottom left. And here we have in the top right 2x2 tile size instead. So our shader that is determining the shading rate has had to spit out a second shading rate image at much higher resolution, one value for every 2x2 pixels. There's a slight cost to doing that. And then in the bottom right we can see a significant reduction in the number of lighting calculations when using 2x2 tile sizes. Particularly what you'll notice here is that the number of full rate tiles, which are in red, has significantly reduced. There's far less reduction elsewhere in tiles that are 16x16 tiles that needs 2 or 3 waves. There really isn't much of a reduction. But there's a huge reduction in the number of tiles that need all 8 wave 32s to run. And before we get to the performance figures, here again is our debug where I don't do any hole filling. So here is the 8x8 tile size, and we can see just how many lighting calculations we're doing. And then for 2x2 tile size, we can see that there's been a significant reduction in the number of lighting calculations for this scene. So the all-important performance figures, how did we do? So if we take that scene with no variable rate shading and no sparse lighting, the entire scene took 6.5 milliseconds to render, of which 2.6 milliseconds was the deferred lighting time. Now if we turn VRS on and we turn sparse lighting on and we're lighting with the 8x8 tile size, this time drops significantly, down from 6.5 milliseconds to 4.4, of which the deferred lighting time was 1.69. So our deferred lighting has dropped to 64% of the original time, the original deferred lighting time. When we go to a 2x2 size, we're saving a bit more. So our total scene time has dropped to 4.1 milliseconds. Deferred lighting time has dropped to 1.38, and deferred lighting is now 52.5% of the original deferred lighting time. So there are some overheads from running with 2x2 tile size. We have to output this second higher resolution shading rate image, and of course we're reading that back in. It's a bigger image, requires slightly more bandwidth. However, that's significantly outweighed by the reduction in deferred lighting calculations. So moving from an 8x8 tile size for lighting to a 2x2 tile size, deferred lighting we shaved off another 11.8%, and we had only 40 microseconds of overheads versus 310 microseconds saved. So in real wall clock terms, that's a 270 microsecond win. And the really great thing about 2x2 tile size is that it really helps when we have a worst case scene, when we have a lot of full rate tiles. This is where it breaks down those full rate tiles. It doesn't help a great deal if we've got a lot of low rate in the scene, but that's not a worst case image. So variable rate compute shaders, and how did we do? So if you remember the goals from the beginning of the talk, I'm sure you will agree there was little or no perceptible quality loss. We have managed to preserve single pixel details from whatever source they might arise, whether it was lighting or whether it was a single pixel of snow. we significantly reduce the number of deferred lighting calculations. This really helps, particularly with ray tracing, where people often cite that they can only afford to launch 0.5 rays a pixel. We're guiding the lighting calculations to where they need to happen, and where we're just wasting our time producing essentially the same value between multiple pixels. The light list is still wave invariant. We have each wave is processing the same 16 by 16 tile, so we still get the benefit of having a uniform load of the light list processing the same light for all those pixels. In this case, we have applied this to deferred lighting. It could be applied to any full screen pass. It's easy to modify any shader with the prefix and postfix functions, and just reuse the buffers we've built and the lighting count we've built. And finally, we have a low fixed overhead. You do not have to have, say, very many lighting calculations at all for this to be a net win. So it's very hard for this to be a net loss, in fact. And the nice thing, of course, is that variable rate shading has a positive feedback loop. So the higher the resolution, the lower the visual error, the more you can share those lighting calculations. So in reducing the costs of both shading and lighting, we can help push resolution even higher, and this is our positive feedback loop. So the rest of this talk is really a bit of a bonus. We've covered the core techniques of variable rate compute shaders, particularly applied to deferred lighting. So I wanted to just spend a couple of slides talking about this visible feature where we can see the wireframe and exactly why that is, and some opportunities for further development here. So it's a design requirement of variable rate shading that edges are always shaded at full rate. This is due to coverage, to make sure that we get perfect silhouettes and we don't have the kind of checkerboard problems with silhouettes. We don't need to rely on temporal AA in the same way to fix that in what usually turns out to be quite a soft look. However, this is the trade-off, is that we have this overshading on edges. Sometimes you need that. As I said, sometimes it's a silhouette and you must do it for quality. But sometimes that edge is an internal to a surface, and ideally you wouldn't be overshading it, or you certainly wouldn't be running all those lighting calculations, because this is an edge on a bunch of triangles that are approximating a continuous surface. And that's for terrain, that's everywhere. Most of those edges, we don't need to be doing all those extra lighting calculations. So this should be quite simple to fix for a terrain. All we need is one bit somewhere, whether it's in a GBuffer, whether it's a stencil bit, that says this is a terrain pixel. And then all we have to do when we're building the buffers to light is, instead of saying is the coverage the same, whether that's with the plane equation or whether it's the coverage bits in a GBuffer, we could say, well, both these pixels are terrain pixels and the depth is extremely similar, therefore we're just going to share the lighting calculation. And this should be very fast to implement, and would help a lot with terrain. Unfortunately, this is a bit more difficult to solve for general mesh rendering. We have two triangles with different coverage but very similar depths. How do we know that it's you're allowed to share lighting calculations across a particular edge? This could be done, as I mentioned at the start of the talk, with inexact GBuffer examination. However, this is very slow. So to speed this up, we need, I would suggest, some kind of ID buffer where, say, we have bits for whether this is terrain and can share lighting calculations, whether it's skin and it can share lighting calculations, whether it's some other surface that can share lighting calculations. There are some parallels here with the checkerboard problem of we have a hole, what do we want to fill it with, which surfaces should I consider on the adjacent pixels and which should I not, and there's been some talks about that, particularly Dice did a talk showed an ID buffer for doing exactly this. So in the sparse lighting system I presented in this deck, there is an obvious inefficiency, which is per 16 by 16 tile, assuming you're not lighting every pixel, you probably have one partially filled wave. So you have a wave with a bunch of threads turned off because the number of lighting calculations required for that tile wasn't an exact multiple of 32. So this is clearly an inefficiency. The one way to improve on this inefficiency is to use a larger tile size. So we still have a maximum of one partially filled wave per tile, but we have far less tiles for the screen. Whether this is desirable, you obviously get a decrease in efficiency for light culling, for example. So this is exactly where your sweet point for your tile sizes might vary, but I would suggest 16 by 16 is a good number. The other, a completely different option, if you don't get or you don't think you derive a significant benefit from this spatial locality where all the threads are processing within the same 16 by 16 tile and you have uniform data. If that's not important to you, an alternative system is that you just have a simple buffer which has the XY coordinate, the absolute XY coordinates of all the pixels that you want to go and light and account. This is going to be slightly slower to produce because you're going to need atomics, but you only have one count for the entire screen, so you only have a maximum of one partially filled wave for the entire screen. But you give up completely on you're going to need less waves to light your scene, but there's now no guarantees at all about spatial locality, and even within a single wave you might pick up threads which are processing very different pixels spatially. So we now come to the last part of the talk, which is a little bonus material on VRS deblocking, and that is looking at the VRS squares artifact as a post-process and attempting to fix it. So quite simply, we're looking for where variable rate shading has put down duplicate values, and possibly sparse lighting has done the same. We need to preserve edges, we need to preserve depth discontinuities, we need to preserve full rate shading and not interfere with that. That's critically important. And of course the last point goes without saying, this needs to be fast. So the source code is available for this. The shaders are available in our VRS and Sparse Lighting Xbox sample. So I'm not going to spend too long going over the exact algorithm. I'm just going to touch on it briefly. So the first thing we do, common optimization, is we load color data in blocks into group shared memory. And then we work on a separate horizontal and vertical passes. So we're looking at a 3x1 kernel or a 1x3 kernel running over this data. If the central color is close or dissimilar to its neighbor, then, it's the same or dissimilar to its neighbor, then we do nothing. If the central color is very close to its neighbor and close both in terms of color and depth, then we blend the colors, possibly with some local sharpening. Otherwise we do nothing at all. So what does this look like? Well, we have in the top left here, we have the source image where we're running variable rate shading, and you can see I've highlighted two areas in green where we have VRS squares in effect. You can see a lot of the image is running at full rate, where we have different values for every pixel. So on the top right we have the ground truth, and we can see a lot of this full rate stuff is completely the same, but in the highlighted areas where we're running at a low rate, we can see there's a bit more detail in there in the full rate. The bottom left we have simply a blur. So we're applying the blur where we're finding this duplication of values, and we can see that it has removed the squares artifacts, but yes, it looks blurry. And then in the bottom right we have this sharpening, which you can debate how much this helps the approach to the ground truth, which is the image above it. And we are applying this shader to every pixel on the screen, so we can see that it is only tackling the areas where we have some artifacts. So we've correctly identified those areas where we could do something to improve the quality as a post-process. So the question arises where to fit in this shader, and we can't really apply it to the GBuffers. That's too many buffers and the data is not necessarily filterable. So we need to do it really after lighting, after we've got to the point we only have one buffer to deal with. But we need to fit it in before per pixel variance is added, and this might be from transparencies or post-processing. The other thing is that this shader is quite memory intensive. The amount of math is very low. So if we can combine it as a front end to some other full screen pass, we can make this go a lot faster. So in fact, in my demo, I only have one post process, and that is tone mapping. There's nothing else in there, largely because, you know, for a sample you want to see the pixels unaltered, or largely unaltered. So here are some timings. So deblocking as a standalone pass, as I mentioned, mainly memory bandwidth limited, quarter of millisecond. The tone map shader similarly is memory bandwidth limited, so 0.2 milliseconds for that. So the total amount of time to run both these shaders standalone is 0.46 milliseconds, but combining them into a single pass, I get 0.29 milliseconds, so I get a considerable saving from having this deblock occur as a front end to an existing shader. It's only costing me 79 nanoseconds. So has this post-process deblocker done what it was designed to do? The answer is yes and no. It does remove the VRS squares artifact. It does leave areas of full rate shading alone. It does preserve edges. It is fast. The problems, of course, are that the sharpening filter, you always have to be a bit careful with sharpening, or you can end up distorting things and ringing artifacts. It's a post-process fix-up. It doesn't introduce any new information. So this is where something like temporal AA, this is the reason temporal AA is the best AA, is that it, compared to, you know, post-process fix-ups, is that it in TAA injects new information. We're simply not doing that. The main issue with this, and your results might vary, you can try it, is that because it's a post-process fix-up, it has very poor temporal stability. Whether you notice, of course, that's the thing that you want to check, because obviously you're only reducing the shading rate in areas of the frame where, by definition, there is low frequency detail, and the eye won't notice. So this I think is another tool in your toolkit to try out. So wrapping up the talk. So sparse lighting or variable rate compute shaders is a very powerful new technique to reduce lighting operations, and this means reducing the number of rays you fire. We're taking advantage of the fact that we know there are areas of the screen where we can reduce the frequency of lighting. It's the frequency of all shading operations, and this is driven by variable rate shading. In our case, we got significant wins in the sample that you can download from reducing shadow ray counts, reducing atmospheric scattering, reducing global illumination calculations. Of course, this can be extended. We're not just talking about deferred lighting. Any screen space technique can use this. So particularly attractive might be a shadow mask, screen space EO, screen space ray tracing, screen space GI, fog. It's extremely easy to integrate. We just have 2 additional function calls to wrap your existing shaders. We have a prefix and a postfix. Other than that, your shaders are exactly as they were. Potentially it can be faster if you don't need this invariance, this spatial locality. There is, as I've mentioned, an alternative system of just writing out the pixels to light for the whole frame, and you only get one partially filled wave that way. And then finally, we have this idea of fixing the blocking issues as a post-process, which your mileage may vary, but I think this is worth a try for people. And that's it. Thank you for getting this far. Thank you particularly to Christopher Wallace and the awesome rendering team at the Coalition for sharing their variable rate compute shader implementation and the wins they got from it in Gears 5. And as mentioned, registered Xbox GDKX developers can download the sample with all the source code for this talk. Thank you very much.